Hello, everyone, and welcome to Moments with Atmospheric Vapor. My name is Amin, and I'm here with my colleague Shahnawaz.
Hi, I'm Shanawaz. I'm an associate research professor here at ASU, and I'm
Thank you.
excited to join you today.
Thank you. Today, we are very excited to have a very special guest with us, Mark Molinaro. Mark and his team are working on new ways to make water from air. Mark, welcome to the show.
Yeah, hey guys, thanks for having me on. I appreciate it.
Thank
I'm
you.
Mark Molinaro, founder and CEO of SkySpigot. Our mission is to change the way the world gets its water by creating the best atmospheric water generator on the planet, one that creates the most water using the least energy anywhere on Earth.
Wow, that's a very powerful mission, and I'm sure our listeners will be inspired. Let's go to our first question. What stage of development is SkySpigot in?
Yeah, sure. We're a pre-seed, self-funded, US-based small business. And over the last 18 months, we've studied just about everything we can on water, from its atmospheric dynamics to its molecular properties. We've looked at existing tech and some pretty cutting edge stuff too. All this has led to a unique design that we believe will transform the industry. Right now, we're launching a prototype supported by a provisional patent with innovations that set it apart from anything on the market. We finalized a project plan covering research, staffing, procurement, assembly, and testing. We're targeting a 1-year timeline to complete it, and we're actively looking for partners and investors.
That's very exciting, Mark. I like how you explained the careful research and the plan for prototype. It shows real progress and commitment. Thank you. And the next question will be asked by Shahnawaz.
Hi, Mark. Like from Amin, I understand that you come from a very different background. You were in IT first and for many years, and now you are in water. And my question is, how did you get interested in water, and especially water harvesting? And please also share the story about your transition from IT of creating your own company, SkySpigot.
Yeah, sure. So, yeah, my roots are in IT, like you said. After about a 30-year corporate career, I launched an IT services company in 2003, grew it over the next 15 years to the largest US-owned nearshore IT services company. Along the way, we earned 5 Inc. 5000 awards for growth. And in 2018, I sold it and retired.
Good for you.
I ended up doing what a lot of people do when they retire. Built a beach house in Florida, lived there for a while, didn't really settle in, and eventually moved here to Colorado. But anyway, it took me a while to learn that I wasn't really good at retirement. It turns out I wasn't cut for leisure, and I needed a challenge. So I wanted to do something impactful at this stage in my life. So I started digging into the global water issue. The genesis of that was that I have a shared well system here in my home in Durango. And I purchased a lot on the other side of the county and realized that having a well there was going to be an issue. The west side of the county where I currently live has adequate water under it, but the east side doesn't. And both are outside of Durango's municipal water system. So I looked into alternatives, none of which were really very good. And that's when I learned about AWGs. So it started out a bit personal for me. But anyway, as I dug in a bit further, a few things became apparent to me. Here in the US, it's easy to take water for granted. But elsewhere, access to clean, reliable sources of water is a daily struggle. So that kind of checked the impactful box for me. I did a deeper dive at that point into how AWGs worked. And in looking at existing technology, I thought that there was ample room for innovation. I also thought it would be an interesting puzzle to figure out, one where I could make an impact and one that has a global reach. So between all of those things, I was all in. And like I said, I come from a commercial point of view. So the first thing I did was write a business plan, of course. I commissioned a global research study that analyzed usage, the split between industrial and residential AWG use, the economics, forecasts, and some of the key players in the market at around $16 billion by 2030. And as the business plan evolved, it included all the typical things that you'd have in one: the addressable market, financial projections, marketing and sales, staffing, and all of that stuff, all of which eventually boiled down to a list of design imperatives. At that point, I felt like I had taken the business plan as far as I could and needed to actually design a device to meet those imperatives before the business plan could go much further. So the next step for me was to hire a small team of engineers to dig in. Like I said, we conducted in-depth research of water's behavior, looked at existing AWG tech, researched innovative alternatives, and now have a theoretical design. The overall goal, as I stated earlier in our mission statement, was to create a device that could generate water in substantial quantities anywhere on the planet and do so at energy costs that would open up new markets. It's kind of interesting when I looked at that research study, I took it at face value. 16 billion by 2030, good enough to move in. But when I took a deeper dive on the current technology, it became apparent to me that the scale was off by orders of magnitude. And I kind of liken it to the transportation market, but with only trucks having been invented. So I thought if we could invent the equivalent of a car, we could transform this into a $1 trillion market, a multi-trillion dollar market. And I believe we will. Our approach is different from a lot of other competitors. Many of them started out as research projects in government or university lab settings where science was the thing. When it seemed like the resultant tech that came out of it could be applied to a real world problem, like water generation, there was a movement to bolt on a commercial wrapper and take it to market. Oftentimes, the founders are PhDs in applied science, and sometimes that continues to be the focus of the company. But that's the absolute reverse of how we approach things. We started off as a commercial endeavor and developed the tech to fit the business plan, not the business plan to fit the tech. And you get a very different result when you start with a business plan and whittle it down to a device than when you start with a device and retrofit a business plan around it.
Okay, thank you very much, Shahnawaz and Mark. I have a question here. How did you arrive at your atmospheric water generator design? And let me know, what is it exactly?
Sure. First, let's clarify what it's not. And since AWG technology can be a little bit complex, let's have some fun and use baseball as a metaphor. First of all, 90% of AWGs worldwide rely on vapor compression technology, a method dating back to the 1960s. It works by blowing air over a cold coil to produce water, and it's very simple and it's very effective. However, at the same time, it's highly inefficient and thrives only in moderate, humid climates. Think of an aging pitcher with a tinge of bursitis. He might do well in Atlanta in the spring, but he's going to struggle in Denver in October. Next up, metallic organic frameworks. They're fairly new. They have a high affinity for water and a low desorption energy, which makes them, at least on paper, ideal for AWGs. But they're also expensive and they're difficult to source. And there's still some questions about their longevity. You can think of them as rookie star athletes, flashy, but a bit untested. They may hit more home runs, but at their salary, you might not be able to field the whole team of them. Our AWG harnesses a molecular sieve called zeolite, synthesized from clay, which is both abundant and affordable. Zeolite absorbs slightly less water than MOFs and requires slightly higher desorption energy, but with some pre-processing, some additives, and post-processing, it nears MOF's performance. Zeolite is like a squad of veteran ball players, consistently knocking out singles and doubles on the cheap. Cool thing about zeolite is it can also be manufactured from waste materials. And that's an interesting way to benefit the planet. Fly ash, a byproduct of coal combustion, can be made into zeolite. The cellulose and synthetic fibers of recycled clothing can too. Likewise, polluting materials like plastics and industrial slag and waste glass can be converted into zeolite. All in, this allows us to source zeolite anywhere on the planet and reduce landfill deposits and lower carbon emissions. I think prospective customers, especially Fortune 500 companies committed to net water neutrality and sustainability goals, will be totally on board with this approach. So zeolite is typically structured in packed beds or coated on fins or wheels, and MOFs pretty much the same thing too. Fins, however, are 100% redundant, and they're completely absent from our design. And packed beds, they work, but they grapple with airflow and desorption issues, making them somewhat less than ideal. So I can't go into too much detail, but our approach is very different and in many ways groundbreaking. The way we fabricate and integrate zeolite into our adsorption desorption cycles is unique. Our design slashes energy use, is infinitely scalable, and can generate water across diverse climates. And I think it'll set a new benchmark for the industry. As I mentioned, I call Durango, Colorado home, where the winters are cold and dry and the summers are hot and dry. And Durango is a pretty good proxy for the Arabian Peninsula and areas of Africa and Asia where the crisis is worst. Our modeling suggests our two-tower system will work well in any of those locations, producing an average of around 500 gallons per day at an energy cost of under a penny a gallon. And like I said, that's just a single two-tower system. By adding tower pairs, scalability is limitless. And, we don't split our focus between water generation and dehumidification or cooling. One mission can dilute the other, and there's always trade-offs when making technical decisions between two competing factors like that. Our sole focus is water generation, nothing else. If someone wants to use our device to dehumidify, fantastic. We may even be the best device for that. I have no idea. But that's not the business we're in. We make water from air, period.
A very clear explanation, to be honest. And I like how you use the baseball example and the idea of turning waste into zeolite. Is fantastic. Shahnawaz?
Thank you, Mark. Yeah, very interesting conversation. I very much interested that you're using a very traditional but a modified zeolite for your system. And so I was wondering about how is your theoretical design is different from the existing devices. And I understand you're playing with some interesting interplay, like adsorption, desorption, cycle, convection, conduction. Can you elaborate all this stuff, in a simple manner, so we understand your system a little bit more?
Absolutely. Absolutely. All right. So first, need everybody to buckle their seatbelt because this is going to get a bit nerdy.
Okay, we are ready for it.
First, there's really no comparison between our design and that of any vapor compression system, so I won't offer one, except to say that cooling 100% of an airflow to liquefy 1% of it that's water is like having a giant walk-in freezer to house a single ice cube. For MOFs and other adsorbent-based devices like ours, there are two half cycles: adsorption, where water vapor molecules are taken up, and desorption, where water vapor molecules are released. And unlike vapor compression devices, the goal is to first concentrate water vapor molecules and then act on them versus acting on the entire airflow. Use much less energy that way. So now for the nerdy part. Adsorption takes longer than desorption. It uses less energy and generates heat, while desorption happens comparatively faster, uses more energy, and requires heat. That makes for some really cool interplay between these two half cycles. The common thing to do is make them both the same duration. But since desorption is faster, once complete, that segment of the device is waiting for adsorption and is idle. We take advantage of that idle time in two ways. First, while the desorbing chamber is waiting to start, we preheat it with the heat coming off of the adsorbing chamber, which, as I said, generates heat. And second, at the end of the desorption cycle, we immediately begin the next adsorption cycle, since that's what's coming next anyway. Another challenge we've overcome is the problem of when to start and stop each half cycle. The thing is, adsorption isn't a linear process. As time moves forward, there's a diminishing uptake as fewer and fewer water vapor molecules are adsorbed. Many devices are time-based, guessing at a good stopping point, and perhaps even using absolute humidity to arrive at that guess. We actually measure every uptake that's done in the adsorption half cycle and water removal on the desorption half cycle. That way we know exactly when to stop and start each half cycle. Less wasted time equals more generated water at a lower energy cost. Another really cool thing that we've done is to re-vector heat from the desorbing chamber to the input airflow on the adsorbing chamber in cold weather. This allows us to obtain more water when it's really cold outside and difficult to do the process. There's also a structural gap in our device between the fan and the zeolite. We fill that with an inexpensive silica gel insert, which not only boosts water production, but it generates additional heat as well. And we don't use compressors to create a vacuum or partial vacuum during desorption. There's an energy cost to that, so we avoid it altogether. We also don't blow hot air to desorb. Our desiccant and heat source are integrated in such a way that that's unnecessary. We use conduction versus convection, which is much more efficient. And the next one is one of my personal favorites. So water vapor is coming off the desorbing chamber at a fairly high temperature. Condensing it requires us to drop that temperature below the dew point, which in most cases is at or above ambient air temperature. This means that at certain temperatures, actually a pretty broad range of temperatures, phase change from gas to liquid happens with zero energy cost. It's a really cool and overlooked advantage of using zeolite's higher desorption temperature. Whereas MOFs, which have a lower desorption temperature, rely on artificial chilling in most cases to phase change, which requires energy. And before we get off the subject of MOFs, a lot is made of their low desorption energy, and it's true, 100%. But while that's an interesting metric, it might not be the most important one. If you're efficiently revectoring heat generated from adsorption to desorption, like we are, it's the delta between those temperatures that matters. And lastly, perhaps the biggest advantage of our design can use waste heat from external sources, which brings the cost per gallon to near zero. That's something vapor compression technology just can't do, since they actually generate waste heat.
Interesting. It's impressive how your design reduces waste energy and makes the system more efficient. Let me ask a question here. What are some use cases for your device?
I mean, close your eyes and think about all the ways water is used today. It's a pretty exhaustive list. So the use cases for our design are really only limited by your imagination. But let me give you a few examples, ones that aren't really talked about that much. Everyone goes to grocery stores, and I'm sure you've noticed and about a third of all the aisles have either a refrigerator or a freezer unit. The thing is, for every degree of cold air they generate, there's an offsetting degree of hot air that's vented out. Now imagine a forward-thinking grocery store that reuses that waste heat in a SkySpigot AWG to create water. It's the same for data centers and many other industrial processes that both need water and generate waste heat. They can use that waste heat and generate water for next to nothing. Same for high-rise residential complexes and businesses with HVAC units on the rooftops. They can turn that waste heat into water and reduce reliance on municipal supplies in the process. Or how about a microbrewery that uses AWG water to brew their beer? People would buy it just because of that. Car washes are another great use case. Solar homes with solar panels. I just learned that beyond whatever is used in the household, only 30% of what remains that's generated by the solar panels can be fed back into the grid. The rest is just shunted into the ground and wasted. Homeowners can use that electricity to create low-cost water. And if you've got solar panels on your home and not a SkySpigot AWG, something is very, very wrong. Then there's desalination. Everyone's aware of it, and plants are popping up across the globe. Desalination can be a great large-scale way of providing water to coastal areas. In every case, though, getting the water beyond the plant requires piping or trucking. This takes what should be a low-cost water generation mode and cranks the real cost to the end user to around 5 cents a gallon. Now imagine a farm of SkySpigot AWGs anywhere in the world, placed exactly where water is needed, generating the same quantities of water as desalination for a fraction of the end user cost.
Amazing examples. Show how flexible and useful your device can be in many real-life situations. Okay, Shahnawaz, may you please ask your question?
Yeah, I agree with you. I would like to thank Mark for sharing and being so candid, and sharing some of the example of application from grocery store all the way to desalination. This is very interesting. So my next question is, as a successful entrepreneur, before you were in IT, you ran a large business. Now you're a founder and a CEO of a SkySpigot, and as an early stage startup, what are some of the challenges you will need to overcome, in establishing your company?
Yeah, it's a great question, and there are quite a few. On the operations side of things, of course, funding, and along with that, dilution. Scope and speed to market have to be balanced out. And as a startup, spend control is always a big concern. Building awareness is also a slow process too, believe it or not. I mean, it's funny, everyone understands water, but somehow the application of atmospheric water generation is largely an unknown. On the tech side, prioritization is key. Like I said, we looked at some pretty interesting tech that might have been included in our design, all of which have trade-offs and varying degrees of readiness. For example, we looked at how different wavelengths of light and electromagnetic fields interact with water, and how to take advantage of water's dipole structure, and even cavitation as a novel phase change mechanism. And any of these ideas at some point could be part of a novel AWG design. I mean, you look at each of them because they're interesting and they offer possibilities. But if you want to get a device designed, you can't spend all of your time on possibilities. Another thing we wrestled with was which desiccant to use. We looked at all of them, but we arrived at zeolite, not because it was the best performing desiccant, but due to its abundance and cost, it was the best commercial desiccant.
Before asking another question, I should point out one important thing. In the last year Atmospheric Water Harvesting Summit, we decided to call it AWH, and Atmospheric Water Harvesting.
UFO, UAP, tomato.
Yeah, you're right. You mentioned spend control. How do you get high level technical and operational support without blowing a hole in your startup budget?
Yeah, that's it's really important. First, I'm a pretty quick study, and if I find something I'm interested in, like in this case, AWHs, I'm going to be an expert pretty fast. But like I said, my background is in IT, so I knew I had to bring people in with engineering, chemistry, and physics backgrounds who could advance our project. I've got an operational background, but within service businesses, not product companies. So it was important for me to find people who had outsourcing, supply chain, manufacturing experience on a global scale. To make that happen, one thing I did early on was establish a board of advisors. Since we were in a research heavy phase at the time, the experience I was looking for was more weighted towards tech, people with advanced degrees in chemical engineering, for example, in addition to others with a wide variety of technical experience. I wanted the most diverse set of talent I could get on the advisory board. And it's kind of funny. I posted an ad on LinkedIn for advisory board candidates. And to my surprise, in just a week, I had over 400 of them. And they were all highly credentialed and experienced. The thing they all had in common was a deep understanding of the global water issue and a strong desire to play a part in fixing it. And they all share the same passion that I have in democratizing water. It's personal to all of us. And as we move from research to prototyping and production, I've recently initiated another search, a second one for advisory board candidates. I had to shut that down after 4 days because of the volume of candidates. This time I'm looking to fill gaps in finance, access to capital, materials, legal, and sales and marketing. And once again, I've got an incredible short list of potential candidates.
So, Mark, this is like great for you. You were able to get highly credentialed and experienced advisory board. So this is all done. Now you're looking for more experienced business and finance people, and good luck to you. And
Yeah, thank you.
yeah, so my next question is like, what does the global atmospheric water harvesting future look like to you, Mark? You already shared some of them,
Yeah,
but we'd like to see a big perspective, like what do you think the future
yeah,
will
sure. Sure. So first, I see the driest regions of our planet getting abundant, clean water from the sky.
be?
I can imagine wealthy nations like ours generously sharing AWG technology with developing countries, much like they currently provide economic or defense aid. I see companies that have pledged to go net water neutral actually pulling it off, turning air into water and meeting the commitments they made publicly. I envision water extending further as a tradable commodity, like pork bellies, natural gas, or soybeans. You'll see water farms pop up across the globe, just like you see wind and solar farms today. Water credits will be traded just like carbon credits are. I see AWGs extending municipal water supplies, bringing not only water to parcels that would otherwise remain undeveloped, but trillions of dollars in GDP uplift and billions of dollars in incremental tax revenue collected in return. Home designs will take into account water production, the same way they account for heating and cooling and cooking and washing and cleaning today. Any device that generates heat will have that heat refactored to a household AWG, offsetting the need for a municipal water supply or wells. Yards with beautiful green grass will make a comeback. Flowers and vegetable gardens and dog parks too. AWGs will provide water for cattle, pigs, chickens, and every other kind of livestock. I see Native American tribes whose once clean groundwater, polluted by mining since the 1940s, now receiving clean water from air. I see wells being replaced by AWGs, allowing the world's depleting aquifers to regenerate. I see every data center, every grocery store, and every industrial process that both generates heat and uses water, leveraging AWGs like ours. I see millions of tons of fly ash, glass, and other waste transformed into zeolite, slashing landfill waste and cutting carbon footprints. And most of all, I see atmospheric water generation as a global multi-trillion-dollar industry, and SkySpigot emerging as its leader.
Well, thank you. I mean, this was beautifully said, like your vision, like where we are and where we want to go and how we are and what we could become, and how you also think about helping people in places, where they don't have any water, good quality water. So thank you for sharing all this beautiful, vision that you have. And I hope all of this become reality for you, me, and everyone else,
Thank you. It was a pleasure.
Mark, thank you so much for your time today and for sharing your journey and vision with us. It was really inspiring, and I'm sure our listeners learn a lot about the future of water from air. Thank you.
Great. Thanks again, guys. I appreciate it.
Thank you, Mark.
And yeah, thank you. And to our listeners, thank you for joining Moments with Atmospheric Vapor. Please follow us for more conversation about water technology and environment. Until next time, goodbye.